So firstly then we will discuss longitudinal control. So we have both the elevators and throttle available to us here. The elevators is going to control our speed, and the throttle is going to control our flight path angle. And each of these controls have differing initial and long-term effects. So what I mean by that is, once these controls have been changed, there is a short-term or initial response which is then left to kind of equalize into a new condition. So that state in the middle between initial and long-term is called the transient response, right? So for example, if the aircraft responds to a throttle input for a fixed elevator deflection, so what we're doing here is describing what happens if we change one of these to a new condition and leave the other one the same, right? So in this case we're going to change the throttle application for a fixed elevator deflection and watch what happens. Well, in the initial stage we get an acceleration or a deceleration, right? So that's a change in forward speed, but long term the speed is regained to the trim or the initial condition, but we get a change in flight path angle, right? So that's that will be more intuitive, or it will be more obvious when I describe some of these charts in a moment. But if we do the opposite thing and make an elevator input at a fixed throttle setting, the initial aircraft response is to rotate in pitch, right? Or in other words, change the flight path angle. But long term, the aircraft will either increase in speed or decrease in speed to account for this new flight path angle. So you can see here we have two control surfaces, two things we'd like to control, and how they're interlinked if we change one and leave the other one fixed, right? So the initial response stage is the aircraft's initial response to the control surface input. Then the forces are allowed to equalize within this transient period here, and then we get this final response once everything else has settled down. So for an open loop system which is monitored continuously by the pilot, let's say our pilot wants to make an adjustment to the speed, the airspeed. So the pilot's going to make a step input to the elevator and hold the new elevator deflection angle. Now, in reality, obviously some of these inputs are going to be continuous. They're not necessarily going to be step inputs, but for convenience of describing the dynamics here, we're going to assume that the pilot makes a step input to the elevator, allows the aircraft to settle down, allow the forces to equalize, and then that's going to allow the pilot to reassess the original input, right? So was the control input made too large, too small, right? So reassess the original input, and then if the control input gave the desired effect to the airspeed, then great, you don't need to do anything else. If it was too large or too small, then obviously another adjustment needs to be made to the elevator, and therefore this cycle or this process gets repeated until the desired airspeed is reached. So let's take a look at what that looks like on some charts. So here are some charts in the Etkin and Reed textbook. So for a given elevator deflection, in this case 1 degree, on a jet transport type aircraft at high altitude cruise, made an initial input or a step input to the elevators, and we get the following charts for changes in forward speed, angle of attack, and flight path angle. Now you can see the difference between these two sets of charts is time scale, right? So this is from 0 to 10 seconds, and then these are the same charts but extended over a much longer period, up to 600 seconds, right? So 10 minutes. So what happens is initially in the first phase of the initial response of the aircraft to a step input on the elevators is of course the short period pitching oscillation, which is what you're seeing here. So a very rapid change in angle of attack, which is very well damped. Has a high frequency, it's very well damped. So of course that is the short period pitching oscillation, right? And what you can see is if you extrapolate that input out is of course now the aircraft wants to converge towards the new condition as defined by the new elevator deflection angle, and you can see that that then turns into what we described as the phugoid, right? So we get the initial spike here, which correlates to the short period pitching oscillation, and then the aircraft, the long-term response of the aircraft is to follow the phugoid trajectory to dampen out that the perturbations as caused by that initial elevator deflection. And you can see that the flight path angle initially changes due to the change in elevator angle, right? But it converges back towards the original flight path angle, right? So remember what we said over here for a elevator deflection at a fixed throttle setting, we're going to change the speed first, followed by the flight path angle, okay? So here we are converging towards a slightly different flight path angle, right, from the initial one, but it's reasonably well damped, that oscillation, okay? And then finally the forward speed changes a lot initially again, but then is reasonably well damped, and we are converging towards this new airspeed, which has some associated delta with it. So again, here we're just looking at basically the initial response on these charts, and the key takeaway here is that we see the short period pitching oscillation within the first couple of seconds, which then develops into the phugoid for the long-term dynamics. And in this case, for this particular aircraft with this particular elevator deflection, all of these oscillations are stable, okay? So let's take a look at what happens if we do the other type of thing and we want to make an adjustment to the flight path angle. Well, we're going to make some adjustment to the throttle now. We make a step input to the throttles, we allow the aircraft to settle in this new condition. The pilot needs to then make an assessment as to whether that throttle adjustment was successful in obtaining the desired flight condition. If not, then you need to reassess and make another adjustment, and so on and so forth. Well, the dynamics are very similar. Again, if we take a look at some more charts from the Etkin and Reed book, this time on page 236, for a throttle input for the same aircraft cruising high altitude. So now we've made a throttle input. So now the initial response is for the aircraft to accelerate, right? Notice as well that this is all at pretty much a constant angle of attack. But now the flight path angle increases, oscillates, but ultimately converges towards a new flight path angle, right? But the speed decays back to the original speed. So the initial response is that the speed changes, the flight path angle changes, but ultimately converges to a new flight path angle at the original speed. So that's just a couple of examples in the longitudinal sense of how control inputs have different initial and final responses. We're now going to take a look at the lateral directional controls.